Hello everyone, welcome to this material characterization course. In today's class, we will look at some of the problems related to scanning electron microscopy. So, these problems will be useful for you to solve some of the assignment problems as well as in the end semester or end of the course examination. So, we will look at some of the problems related to resolution in electron optics as well as the specific system specific problems, and also we will look at some of the applications like in an SEM how we get the resolution and what are the parameters which influence this resolutions. Related to that, we will look at some of the specific problems. So, you will appreciate the importance of these concepts, and then you will just get benefited while solving the assignment problems as well. So, we will just look at the first problem. So, the first problem is when a magnetic field strength of 0.2 Tesla is applied on an electromagnetic lens perpendicular to the electron beam direction with an applied voltage of 20 kilovolt, what would be the radius of the electron beam? And the electron mass is 9.109 into 10 to the power minus 31 kilograms, and the charge is 1.602 into 10 to the power minus 19 coulomb. So, what is that clue we have? We are now talking about the radius of the beam, electron beam. So, the radius is given using this formula. If you recall the electromagnetic lens schematic, we have written an expression in terms of this is a formula. We can use this to obtain this. So, let us solve this, say a simple substitution. We can write by simply substituting this 1 by 0.2 square root of 2 into 9.109 into 10 to the power minus 31 into 20 into 10 to the power 3. We are keeping in volts, and this is the charge. So, if you work it out, what you will get is so you will get something like this, or you can write it R naught is equal to 2.385 mm. So, this is the answer. So, we will move on to the next problem. So, in a microscope, the applied probe current is 3 microamperes, and area of the cross section of the beam is about 1 micrometer. Convergent angle is about 0.02 radians, and what would be the brightness that is possible to obtain in this system. So, now you have the, if you recall, there is a relation between the brightness and the probe current and convergent angles and so on. So, you have to just look back in the lectures the formula for the brightness, and I will write brightness beta So, IP is the probe current and alpha is the convergent angle, and your dP is the cross section of the beam. So, simply a substitution here. So, beta is 3.043 into 10 to the power 9, that is the value of the brightness. Now, we will use this brightness value to solve another problem. So, let me write that problem. The SEM operating kilovolt, the IP and beta values of above, and the spherical aberration coefficient of the electromagnetic lens is 2 micrometer, and what is minimum probe size So, the problem is the SEM operating with 20 kilovolt, having the probe current and beta values of this problem, and then spherical aberration coefficient is about 2 micrometer, and what is the minimum probe size of the electron beam that could be achieved, and you can consider the constant k is equal to 1 and lambda is equal to 0.008 nanometers. So, if you recall the the minimum probe diameter considering the aberration d minimum, which is equal to k Cs to the power 1 by 4 and lambda to the power 3 by 4 times you have IP divided by beta lambda square plus 1 to the power 3 by 8. It is lit. This is the formula we have seen for obtaining the minimum probe diameter. So, if we can substitute these values, let us see what kind of values we are getting. So, this is a simple substitution here. So, 3 into 10 to the power minus 6 divided by 3.043 into 10 to the power 9 into 0.008 square multiplied by 10 to the power minus 8 plus 1 to the power 3 by 8. So, basically we are trying to substitute this, and then you get the values in the range D minimum equal to 8.87 into 10 to the power minus 8. So, I request you to check this with your own calculator, or we can simply say that 88.7 nanometer. So, this is the final minimum probe current we can get if you have the SEM operating parameters in this range. We will solve another simple problem. So, let me read the problem. The primary electron beam current is 1 microampere, secondary electron current signal is 0.3 microampere, and the backscattered electron current signal is 0.2 microampere. What could be the sample current, secondary and backscattered electron yield? So, if you recall, we have a formula for this, a simple formula to calculate this. So, the primary beam current is written in terms of addition of secondary electron signal current, backscattered electron signal current and sample current. So, we can just rewrite So, this is the first answer. The sample current is 0.5 microampere. So, the question number 2 is the backscattered electron yield, which is given by which is eta is equal to I BAC divided by I naught, that is the backscattered electron signal current divided by the primary beam current. So, again we can simply substitute this . You will get again same value. The secondary electron yield, which is written as a delta ISE by I naught, which is nothing but 0.3 microampere divided by 0.1 microampere, which is again delta is equal to 0.3. This is 0.2. The yield is written as 0.2, here the yield is written 0.3. There is no units here. So, a simple arithmetic which involves the concept of how the primary beam current is dependent on the current of secondary electron and backscattered electron and sample current, a simple substitution, and then we can also work out the yield. And we have also seen that the the importance of this, the yield of BSE and the yield of SE decides the contrast that we have seen in the some of the theoretical concepts. So, now we will move on to the next problem. So, the question is, for a given wavelength of electron beam lambda and the spherical aberration coefficient Cs of the lens, prove that optimum image aperture represented in terms of alpha opt is proportional to lambda by Cs to the power 1 by 4. Assume that the net resolution is equal to the summation of theoretical resolution, that is the disk of least confusion plus the disk of confusion created by the spherical aberration. So, how do we go about this? What is the theoretical resolution? Let us consider this R1, which is equal to 0.61 lambda by alpha. So, disk of confusion created by spherical aberration R2 which is equal to Cs alpha cube. So, net resolution if you write let us consider this expression as 1. So, we have just simply put the respective formula and then as per the assumption here we have written the net resolution in the single formula. Now, since this net resolution is depending upon both theoretical resolution plus the spherical aberration, we can write something. So, what we are now saying here is when the spherical aberration is minimized by the use of small aperture, that is alpha opt, diffraction limited resolution becomes worse with the decrease in alpha. So, we have to make a compromise. So, what we can do is so we are trying to see, or we are trying to differentiate this expression with respect to alpha and see what we get. So, you get this so from this we can write alpha opt to the power 4 is equal to 0.61 by 3 lambda by Cs. Alpha opt is equal to 0.203 to the power 4 lambda by Cs to the power 1 by 4, or simply we can write alpha opt is proportional to lambda by Cs to the power half. So, you can substitute this into the equation 1, you will get R opt proportional to lambda 3 by 4 and Cs 1 by 4. So, for optimum resolution. So, R opt is proportional to lambda to the power 3 by 4 and Cs to the power 1 by 4, which gives an expression for this given condition. If you assume this and the disk of least confusion will be proportional to these quantities. So, that is what the physical meaning here. The assumption made here will result in this kind of an expression. So, now we look at another simple problem involving the depth of focus and depth of field. So, what is the depth of focus when semi aperture angle alpha is equal to 0.1 radians and the magnification m of 15,000 x. So, we have seen and this in fact, we have derived this in the SEM class with the schematic. You can recall the depth of focus can be related to this. So, you simply substitute this will be in mm. So, 1.33 into 10 to the power minus 4 mm or 0.133 micrometer. So, that is a very simple problem. Another problem, let us quickly write. So, an accelerating voltage of 25 kilovolts is applied to the tungsten filament in SEM. What is the wavelength lambda of the emitted electrons? So, it is again a very straightforward formula. You have a lambda which is relating to the acceleration voltage. So, very standard formula. We have seen that so straight away you will get 0.00766 nanometer for this kind of a voltage. For 25 kilovolt you will get in this range. And finally, the question is an electron beam refracts at an angle of 0.1 radians when the angle of incidence is 0.025 radians on passing through a region of potential difference V2 minus V1. Does the beam retard or accelerate through this potential difference? If you look at the, or if you recall the very beginning of the electromagnetic lenses, we talked about the Snell's law, and then we said that there is no difference between light or the behavior of light optical system as well as in electron optical system, they are also the same. So, in that respect, if you recall, we have written a formula like this. So, sin I and sin R by sin I is equal to square root of V1 by V2, and then if you recall that schematic where the electrons are passing through the electropotential lens, how whether it is retarding or accelerating depending upon the voltage of the voltage applied to the system. So, we can simply substitute and see what happens here. Sine so, you get V1 is approximately equal to 1/6 times of V2, that is V1 is greater than V2. So, then what happens? The beam undergoes retardation. So, that is what we will see when the voltage V2 is greater than, V1 is greater than V2, then the beam will undergo retardation. So, with all this small numerical problems, I suppose you are able to solve the assignments as well as you are able to solve small numerical problems, and I hope these exercise will help you in the final examination also. If you have any specific queries, you are welcome to interact with us and we will respond to your queries. Thank you.